All right, so now for some more fun stuff. And this is where you really get a hint, a nice, fun little hint of what's to come and why the heck we care about the area under the curve. Because why would you care about the area under the curve? We're going to show you something. Oh, this is the best part of the whole section. All right. The best part of the whole section is going to come in this video. So let's start with example 7. I don't want to write these out, these application problems. You can pause the video and copy them down to your notes, or you can just refer to the video on your own if you'd like. So we have T sub j, and that denotes the time it took to J Van Garteren, I don't know how to say that name, but it kind of sounds like TJ, to ride the 8th stage of the Tour de France in 2014. If there were a total of 21 stages, interpret this sum. Well, all this is asking us to do is to recognize what this sum is equal to. What is this sum equal to? Well, it's T sub, oh, that's the wrong thing. It's equal to, well, T sub 1 plus T sub 2 plus all the way up to the last one. And if T sub j is the time it took for that segment, well, this is the time it takes for the first plus the time it takes for the second, all the way up to the time it takes for the last one. That's just the total time it took him to do the Tour de France. All right. So that's all we need. Okay. So this is the total time for them to complete the ride. That's all it wants you to do. Can you interpret what this notation is signifying in an application scenario? That's the whole problem. That's half of this video. All right, it's not half of this video. You can see how long the video is. It's not half of this video. But material-wise, I don't know. Sort of half. Let's do the next one. So again, feel free to copy this down and pause the video if you'd like. The average annual atmospheric rate of increase. After Calc 1, this should get you a little excited. Rate of increase. We're talking about a rate of change. Rate of change is like slope. Rate of change is like derivative. Okay. The average rate of increase in carbon dioxide, CO2, each decade in parts per million can be approximated with the table below. Estimate the total increase in atmospheric CO2 between this year and that year. Well, how do we do this? We don't know. We haven't talked about this. We didn't talk about this in 1.1, Jason. What's going on? How does this connect at all? Let's not worry about it. You know, sometimes math people, they just have problems that don't have to do with anything, right? Let's just do the problem. We're caring about the total increase. Well, what does the table tell us? The table tells us that every year in this decade, there is an increase of about 1.07. So what's the total increase in just this decade? If every year in this decade it increased by about 1.07, well, then the total increase in that decade was, there were 10 years, and each year it increased by 1.07. Jason, this isn't calculus. What are you doing? Why is this problem here, Jason? Well, let's keep going. Well, we have the same thing. There's 10 years in the next decade, and each year it was increasing by about 1.34 parts per million every year. So this is the total increase in the second decade. Right? This is increase in first decade. I don't know how to spell, but I think decade has a C in it. Plus the second decade, plus the third decade, plus the fourth decade, plus the fifth decade. Hold on. Look what's going on. Does this look familiar? Does this look familiar? I'm going to get really loud here, okay? And in class, I'd be screaming and there'd be people next door and they'd be like, what's going on in here? And you'd be like, don't worry. It's just calculus. It's exciting stuff. Look at what's happening. I tricked you guys again. This is a Riemann sum, right? This we can add it all up together. That part's not important. It adds up to some number. This is a Riemann sum, exactly like we've been doing in the last video. Well, what's a Riemann sum? A Riemann sum is a way to approximate the area under the curve. This is the curve. This is our function. Or should I call this f prime? It's a rate of change. Rate of change is derivative. So the total increase is just the area under the curve of the rate of change. The total increase of something, anything, this can be total, this can be distance, this can be velocity, this can be population. The total increase, the net change of anything, we got a whole theorem on this. The rate of change of anything is just the area under the curve of its derivative. That's crazy. Why does area have to do with total net change? This is why. Because what we actually have here, exactly what we have here, is some function, and we're approximating it with decades. And this function is a rate of change, which we can think of as a derivative. So we can approximate that with the area under the curve to get a total net change. So the answer to the question, why the heck do we care about rates of change? It's because, why do we care? Hopefully we answered that in last class in Calc 1. The answer to the question of why do we care about areas under the curve is that the area under the curve is the net change of any quantity that we want to talk about. We'll talk about this for mass, for distance, for velocity, for basically any kind of quantity that you can think of. There are applications for. And that's why we're doing this. That's why we're talking about this material. Because we're going to be able to calculate some really cool applications using this fact, using derivatives, and specifically, we're going to have to talk about something called an antiderivative, which is undoes derivative, and that's coming up soon. And that's exciting and that's cool. You can put the answer here. The answer is going to be in parts per million, right? If the rate is parts per million per year, the total will be in parts per million. You can fill that in. That's not the exciting part. Let me know if you have questions about this video specifically, because this is the exciting stuff. This is the reason why, and this is where we're going in the next couple of sections. So I'd love to talk about this. All right, but for the meantime, enjoy a video that's only in the single digits of length. But that's cool stuff.